satellite Titania. The photo was taken by Voyager 2 several hours ago as the spacecraft was 92,842 miles from Uranus. This is the NASA Science Report.
NASA Science Report is a special summary of events leading to the Voyager 2 spacecraft's encounter with the planet Uranus. The programs originate live from the facilities of the Jet Propulsion Laboratory in Pasadena, California, and are authorized by the National Aeronautics and Space Administration. The NASA Science Report, Voyager 2 at Uranus, is one of a series of public information programs designed to keep the public informed of space exploration.
Hello, I'm Al Hibbs at the Jet Propulsion Laboratory. We're watching NASA's Voyager 2 make its closest approach to the planet Uranus. This week, we're looking over the shoulders of Voyager scientists as they receive new information on Uranus and analyze it in its original form. We'll be discussing its significance, the mission's scientific goals, and what this encounter can teach us about our world and the universe. At 10 this morning, Pacific time, Voyager 2 passed closest to Uranus, within 50,600 miles of the cloud tops. During the 6 hours before closest approach, and the 2 hours afterward, Voyager 2 has been busier than at any time since it passed Saturn in 1981. In that period, it made its closest approach to the satellites in the rings. Then, Voyager swung behind Uranus, out of contact with the Earth, to conduct radio science experiments. Then, at 4:46 this evening, when the Voyager had, that was 2 hours and 45 minutes after Voyager 2 emerged from behind Uranus, we reestablished clear radio contact with it. It's been busy here at JPL since we talked to you yesterday, and with me to report on all the activity is Dr. Ed Stone, the Voyager project scientist. Ed, once again, I'll ask you, how are we doing? What have we learned in the last 24 hours?
Well, we've, first of all, mainly learned that the spacecraft is doing exactly what we'd hoped it would do, and that we are in the next 24 to 48 hours going to be seeing things that we've never seen before.
It's been remarkably reliable.
It has.
For this ancient, aging spacecraft.
That's right. Well, it's working better in many ways than it did at Saturn, so I think that's an important thing to keep in mind. But we did already manage to confirm that indeed there is a magnetic field. Directly by directly measuring it as we entered into the magnetic field.
This was with the magnetometer.
The magnetometer,
seeing radio waves.
That's right, and also the other instruments which measure the trapped radiation also sense the edge of the magnetic field. So there's no question but what there is a sizable magnetic field. We still have to sort out what its real configuration is, and that's what's ahead for the next day or so.
How long will we be embedded in this magnetic region dominated by Uranus? Are we going to stay there quite a while?
Well, the current estimate is that we may be in it all through Saturday and Sunday, and perhaps leave late Sunday, early Monday. But again, those are only estimates at this time.
We've had pictures of the moons taken several hours ago, but of course our best pictures have been taken quite recently, and they're all stored. And when will we see those?
Well, those come back to Earth tomorrow afternoon, and I suspect that we will suddenly begin to understand some of the features which are quite puzzling, which are showing up in the lower resolution images.
And the other experiments that are looking at both the moons and at Uranus, we have spectrometers and so on. How are they doing?
Well, we did have a very successful stellar occultation, which means that we measured the amount of starlight as the star went behind the rings as viewed from the spacecraft, and that's going to provide us very high resolution information on exactly what the structure of the outer two rings of Uranus really is.
That's the way those rings were discovered from Earth, wasn't it? By watching starlight getting blinked on and off as it went?
Exactly the same technique. From Earth, one is limited to resolving things which are about 3 kilometers, about 2 miles across. From the spacecraft, we can see things which are on the order of 50 feet across.
So we'll be able to see lots of structure in the rings. What's the chances of seeing something with such resolution we can actually measure the material in the ring?
I doubt
big things like Saturn, blocky things like Saturn.
I doubt we'll do that with the photopolarimeter, but the radio occultation experiment, which is going on right at this time, is the one where we actually transmit the radio through the rings from the spacecraft to Earth, and we observe how the ring material scatters the radio frequency. And by working the data analysis, one can interpret that scattering in terms of the size of particles which are in the rings.
The spectrometers have been looking at the surface of Uranus. Have we gotten any better idea of the structure of that atmosphere?
No, we do have some indication that the lower latitudes may be less hazy than the polar region, which is what we may have been seeing. So again, the images which have just recently been acquired and are being stored on the spacecraft may produce a rather different view of the Uranian atmosphere than we've seen from the pole.
We have, however, something of a temperature measurement.
Yes. Well, we do know that that the temperature is to first order exactly what we expect. And now the real question is if we can now resolve separately the temperature at the pole and the temperature at the equator. Again, that same data is currently being stored on the spacecraft so that we can make the temperature map.
Does it appear from these first numbers that the temperature is warmer at the pole, where the sun's been hitting on it for, 20 years?
I think that one would expect the temperature will be a bit warmer at the poles than at the equator, but we don't have an equatorial measurement yet.
Ah, I see. So we're still waiting to get that sidelong view. And I presume we'll also turn the spectrometers on the satellites.
Yes, although I think the main thing we'll do with the satellites is with the photopolarimeter, which will measure the amount of scattered sunlight, which tells us something about the texture of the material on the surface.
Thank you very much, Ed. Uranus, of course, was of interest to astronomers long before Voyager was launched. We knew it was accompanied by 5 satellites. And then in 1977, astronomers using an airborne observatory discovered this set of very narrow rings we've just been talking about. It was hard to explain why the rings were so narrow. Was it perhaps because they were shepherded by tiny satellites? Karen Long talked with Dr. Jeff Cuzzy during a search for those moons.
This is perhaps the first clear image of one of the most exciting new Voyager 2 discoveries at Uranus. 2 shepherding satellites at the planet's outer epsilon ring. It's a 15-second exposure taken some 4 million miles away. According to imaging team member Jeff Cuzzy, the satellites are moving at a rate of approximately 5 miles per second, performing some important gravitational work along the ring.
You can see by their configuration that they act like, it was suggested at Saturn, like sheepdogs or shepherds to confine this unruly flock of ring particles from spreading out in all directions.
Would there just be 2 within the realm of that outside ring?
Well, there may very well be more. As we looked at the images coming down, we all had suspicions of little blips and streaks. There could be other things. And this Uranus system could be very full of junk. For instance, you know that outside of the ring, the main of the ring system in the satellite area, there have been 7 new satellites discovered. And we anticipate finding maybe another 10 or so, within the rings themselves.
The shepherd satellites are approximately 20 to 30 kilometers in diameter. Only 1/2 to 1/3 the size of the newly discovered satellites outside the rings. Why is it the satellites appear long and slanted in the image?
It's slanted because of the motion of the satellite itself, which is about 5 miles per second around Uranus. You can see this star here is smeared less. That's just the motion of the spacecraft. So that's how we tell the difference between a star and a satellite. And the way we know where the stars are is by the navigation team on Voyager has done some very nice work on predicting the location of all the stars that are in each frame. And they can go and very exactly calculate where the camera's pointing and what star we're looking at. So we can actually compare, and measure, in fact, the velocity of the satellite in its orbit.
Voyager 2's cameras will take a closer look at the rings and their satellites toward close encounter.
We have a set of observations which has even higher resolution on the rings than these by another factor of 3 or 4. Okay, but and they look something like this, where the camera frame is stepped across the rings in this sort of fashion. Now, unfortunately, because of time constraints, and everybody else wants to look at other things at this time too, we only have about half of the ring covered. That means we'll take this little patch of 6 and then do it again here, and again here, and again here, and again here.
So we may miss satellites in between.
Right, there are gaps. So it's a bet that you got to take. But if there are 10 or so satellites, then on the average we should be able to get 5.
Interesting, Jeff. It's now assumed that the satellites, rings, and their shepherd satellites were all created at the same time the planet was created. And as we further study these phenomena, we'll undoubtedly learn a great deal more about the formation of our entire solar system. At the Image Processing Lab, I'm Karen Long.
Since the beginning of Voyager 2's encounter with Uranus, we've discovered 9 additional moons orbiting the planet. In 205 years preceding the encounter, we were aware of only 5 Uranian moons. Now we know there are at least 14. Uranus satellites are different from our moon, as Uranus is different from the Earth. George Fenneman talked with Torrance Johnson about the Uranian moons.
Torrance, I understand that the Uranian satellites are very dark. They're supposed to be made of ices. Why would they be dark if they're made of ice?
Well, this is actually one of the things we're going to be looking for in the data that we get back. We know their surfaces are composed, at least partially, of water ice. We've seen the spectral signature of this from data from ground-based telescopes. But they're dark. They're not tremendously dark. They're still, on the average, say, twice or 3 times as bright as the Earth's moon surface is. But that's still dark if you consider that the pure ice ought to be have a very high reflectivity. Some of the other moons we've seen in other parts of the solar system have been very bright with ice. So we're pretty sure that the answer must be that the ice is mixed with darker material, rock or carbonaceous material of some sort.
Oh. What are the sizes of Uranus satellites?
They're sort of what you might call mid-range. The 2 big ones, Titania and Oberon, are about half the size of the Earth's moon. Then there are kind of 2 middle-sized ones, Ariel and Umbriel, which are, again, half again as small as that. And then there's the smallest one of the 5 satellites that were known before Voyager, Miranda, is only about 300 to 400 kilometers in diameter.
Who gives the names to satellites? These names are a little different than, aren't satellites usually named after Roman and Greek gods?
A lot of the earlier ones were, of course, these satellites were discovered a little bit later in history because they're further out. Herschel saw a few of them when he discovered the planet. Others were tracked later. Miranda was discovered in the 20th century, actually, by Gerard Kuiper. The names were historically given by the discoverers with the consent of the international community. There now exists an International Astronomical Union, which has a commission that approves names. So newly discovered satellites now go through quite a long process, actually, of having an international committee look at various possibilities for their names and give them. They usually try to take historical context and cultural context of the pre-existing names into account when they do that.
It seems to come from Shakespeare, though. These, at least some of those.
At least 3 of them are in Shakespeare. Umbriel, I believe, is in Pope's Rape of the Lock.
Well, I wouldn't know. How your study of satellites, how does that help us understand the Earth better?
Well, basically, we're looking at solid worlds, if you will. We're interested in looking at them not only as examples of pre-existing solar system material that formed around these bodies, but as individual worlds in their own right, how they evolved, how they tick, basically. And these things are made of different materials, have had different histories, so they represent what you might call experiments in planetology that we can't do here on Earth. So it helps our understanding of the basic fields of geochemistry and geophysics, the types of things we use to understand our own Earth.
Well, I appreciate your helping me understand a few things. It's been a pleasure talking to you. I'm George Fenneman.
And now, through the magic of live television, Torrance Johnson is with me here in the Blue Room. Torrance, what can we say about the satellites now that we're getting slowly but steadily more information?
Oh, we're now past the point at which they're just sort of unresolved blobs. The pictures that we got back today started showing really not only individual character, but enough detail on the surfaces to give us a lot of enthusiasm and hope that the highest resolution pictures still to come will allow us really to understand the processes going on those surfaces, compare them among the satellites, and to look at them with respect to the other satellites in the solar system.
I'm sure that we have seen evidences of cratering on the surfaces by now.
Yes, as of yesterday, we had seen a lot of things that were splotches that looked a lot like the patterns that are formed by impact craters with bright rays on relatively darker surfaces. But in the data that came back late last night in real time and the data that came back today, we see enough of the craters at higher resolution on the terminator to be sure that we've got holes in the ground. The best pictures that are coming in now, or that came in a little bit later today, definitely show multiple craters on the surfaces and things that are not craters, just as we have seen at the...
you have some evidence of the formations then that are from internal...
There are some things that look definitely like they're, as we say, tectonic features, things associated with internal processes on the satellites. And, of course, we've only got them resolved in the more or less lowest resolution pictures of this sequence now, but the data that's on the tape recorder will, we hope, really reveal a lot to us.
Was this, in any sense, a surprise that they're awfully cold?
Well, we're after Jupiter and Saturn, we are no longer surprised at being surprised. We should be surprised at small cold objects having internal activity, but we've found many examples of Mother Nature figuring ways to do it as we've gone out into the solar system and explored. And one thing we don't know, that we'll have better answers for after we've looked at the higher resolution data, is what are the relative age sequences on these satellites? How do the crater densities, when we do the numbers, compare with the crater densities that we see in the other parts of the solar system, Saturnian satellites and the Jovian satellites, and between the satellites of Uranus themselves? We now know that there are those features there to look at. We suspect there are other things there which can also be dated and dealt with in a geological sequence, and we don't know what surprises that holds yet when we get the best data.
Are we going to have to presume that the cratering process is as intense near Uranus as it is near Saturn and Jupiter? Is there some reason to believe there's a variation through the solar system?
Well, that's one of the questions we have, that there are possible reasons for variation, but the best way to tell that type of thing is, in fact, to look at the satellite surfaces and compare. One of the things that's always intrigued us about the Uranian system, of course, is that it's tilted over on its side, suggesting that the satellites probably got themselves together after that tilting occurred. Now, when that tilting occurred, how long it took the satellites to form after that, with respect to the time scale of the bombardment of the other outer planet satellites, is one of the things we're interested to look at.
Thank you very much, Torrance. We've received literally tens of thousands of pictures from the two Voyagers during the encounters with Jupiter, Saturn, and Uranus. It's a lot different from taking pictures of the family vacation with your pocket Instamatic. David Sparks is standing by in the Spaceflight Operations Facility here at JPL to tell us more about how we get those pictures back here from space.
It is decidedly different than standard photography, Al, although the results are pretty much the same. Good, clean pictures of the subject. Now, let me present the problem to you. You have a spacecraft which is about 2 billion miles away from Earth. How do you take pictures and, in a sense, develop them and then transmit them back home from a spacecraft that has, mind you, been traveling for 8.5 years? Well, the answer to how this is done is just a little bit complicated, but fortunately, Andy Collins, who is a member of the imaging team, shared some of his time with us.
Focus
Cleared some of
using
this
optical
up.
systems onto a selenium-sulfur Vidicon tube, where the charge pattern that results is scanned with an electron beam, converted into an analog signal, which is then digitized and used to modulate a radio signal directed towards the Earth. This signal is received by a sequence of antennas on the ground. It is reconverted back into digital data, stored and processed in computers to represent the scene.
That's easy for Andy Collins to say because he's a member of the Voyager imaging team. But what about putting all of that into terms that are just a little bit more familiar to most of us?
There are two cameras. They have optical systems which aren't altogether unfamiliar to amateur astronomers and photographers. These optical systems focus the light from the target, from the planet or the satellite or the rings. They focus it onto a vacuum tube. It's a Vidicon tube that you see here. The Vidicon tube is used to change the pattern of light which falls on its front surface into a pattern of electronic charge. So from the Vidicon tube, we get an electrical signal where the size of the signal is proportional to the brightness in the original scene. These measurements are converted into numbers between 0 and 255 and are transmitted on the radio link between the spacecraft and the ground. So the picture actually resembles nothing more than a string of numbers that have been coded and transmitted to the ground, the same way one computer might talk to another computer on a telephone line on the Earth. So when Voyager is really churning out photographs, we'll have on the order of 40 pictures strung out between Uranus and the Earth at any one time. There'll be a long, long line of numbers, about 2 billion miles long, and those will be the numbers to compose 40 images. And then the computers then take these numbers and use them to operate film recorders or television sets in which the brightness is proportional to the number that they're looking at. So a high number coming back indicates that that particular location in the image is going to be bright.
Take a look at the photograph on the upper left. The arrow points to a crater. On the upper right, there is a magnified image of the crater. And below, a matrix of numbers which represent the levels of brightness for each portion of the photograph. Zeros mean no light, and high numbers mean bright light. Voyager's radio system returns these numbers to the ground, where computers turn them back into pictures. Land-based telescopes seem incredibly sophisticated in what they have told us, so is it fair to assume that what you're going to measure is going to improve what we know about Uranus?
Through even the largest telescopes on the ground, Uranus is just barely more than a single point of light. So there's relatively little you can learn from imaging Uranus from the ground. Now, Voyager will get so close to Uranus that we will be able to resolve features that are just 2 or 3 kilometers in size. Uranus's diameter is more than 50,000 kilometers, so you can see that there's just no comparison. We will improve the resolution that you can get from the ground by a factor of approximately 1,000 or more.
Pictures from space are, of course, the highlights of each day during the encounter. The imaging scientists, the people in the image processing lab, and finally, the technicians in the photo lab work throughout the day and night to get the best pictures from Voyager ready for the news media each morning. Those pictures are released, along with the other scientific results, at a press briefing each day. Bill Griffith was on hand this morning as Voyager scientists reported on their latest findings.
Voyager scientists had some more answers about Uranus's magnetic field at this morning's press briefing.
We have detected firm evidence for the existence of a Uranian magnetic field, substantial in magnitude and influential over an appreciable region outside of the planet and its atmosphere.
Earlier, it had been estimated that Uranus's magnetic field was about 1/10 the intensity of Earth's, but it turns out it's about half the Earth's intensity and very flexible.
The magnetopause of a planet's magnetosphere is not a rigid boundary, but it's pliable. It's somewhat like having a balloon in which the amount of pressure or total gas inside is variable. And so this magnetosphere can expand and contract, and correspondingly the position of the bow shock will vary as the size of this obstacle to solar wind flow increases or decreases. What are the implications for the interior? Well, it means that there is a conducting fluid inside the planet which is being stirred by some convective motion, regeneratively amplifying a magnetic field which we observe externally. We don't know the characteristics of that magnetic field in sufficient detail to infer yet what the characteristics are of the interior, but after we have the full suite of data obtained from our flyby, we hope to be able to do just that.
Imaging team leader Brad Smith showed this color image of the planet's rings, indicating that the rings labeled epsilon, beta, and alpha are the same color, while rings gamma and eta are different colors. Scientists say that this suggests that while some rings may appear to be the same size, the particles that make up those rings are of different sizes, hence the different colors. Smith also showed this rather intriguing photo of Miranda with an unidentifiable chevron-shaped image on the surface. The good news is that when Voyager focuses on that region during its closest approach, it will produce the highest resolution images of any surface Voyager has yet photographed during its mission. And the best is apparently yet to come as Voyager begins sending back all the information that it gathered during this morning's closest encounter. With today's press briefing, I'm Bill Griffith.
Anyone who's ever taken a snapshot knows you need enough light for the camera to work properly. But what are you to do when you're 20 times farther from the sun than we are here on Earth? When the sunlight on a bright day is only 1/400th as bright as it is here for us. The Voyager team figured out a way to solve the problem, and Dick Laser, the project manager, is here with me to explain it. Dick, how can you tackle a problem like that? You can't change the film.
Yeah, well, let me generalize the problem a little bit. We have to worry about blurred images, about smear. And there's 3 causes of smear that we worry about. 1 is long exposure times, and I'll get to that in a second. 2 is moving the camera. These are the problems that your everyday photographer would have too. Camera motion and then target motion, like taking a picture of a race car. Let's talk about the long exposure time.
Okay, fine.
Uranus is twice as far away from the sun as Saturn. That means, inverse square law of physics, 1/4 as much light falls on its surface, or the cloud tops. That means 4 times the exposure time. There isn't a darn thing we can do about this. We're out of luck. We don't have headlights on the spacecraft or a big strobe or anything like that. We're stuck with that one. The other two we can work with. Okay. In order to explain spacecraft motion, I have to talk about the spacecraft a little bit. The spacecraft is a 3-axis stabilized spacecraft, 3 orthogonal axes, and the spacecraft tips back and forth in each of these axes, and each time it reaches the edge of a deadband, one of these little thrusters is commanded to fire, and then it drifts off in the next direction until it reaches the edge of the deadband and then fires again, and so on. The time period between each pair...
Those are the control limits.
Those are the control limits.
The sensor knows when it's gotten that far, it
That's
says
right.
do something.
These limits are set at plus and minus 5/100ths of a degree.
It's rather small.
That's right. And then one cycle is about 4 minutes across, typically. And as I say here, the typical spacecraft in yaw, one of the pitch, yaw, and roll, the 3 axes, is about 5/100ths of a degree per minute. And if we compare that with the rate of motion of the hour hand, the little hand, on your clock, it's about, you can see, 1/10 the amount.
10 times slower.
10 times slower than the hour hand of the clock.
Like that.
Okay, now let's...
But you're not satisfied with that?
We're not satisfied with that by no means. We worked hard over the last few years to overcome this problem. And what we did was get right down into the heart of the attitude control system of the spacecraft, and we modified the software on the spacecraft so that we reduced the electronic pulse that controls the actuation of the thruster. And as you see in the chart here, this is the same as before. That's the normal pulse firing. What we did was reduce the number of molecules of gas that come out of that thruster each time we fire, so that in fact we've doubled the time between firing.
The drift rate is so much slower.
That's right.
I understand to do this, you actually took the identical kinds of thrusters that are on the Voyager out of bonded storage someplace here and requalified them for space use.
At this particular mode, this is a completely different use of the actuator than we ever planned to do back in 1970.
You're not just redesigning the computer, you're sort of re-engineering the spacecraft.
That's right. Absolutely.
Okay, so that means slower motion.
Slower motion.
So one of the causes then is
eliminated or reduced by 50%.
Okay.
By that fact. Okay. Another unique problem that we have with this spacecraft is that each time that this little tape recorder, it's a little bit bigger than your home cassette recorder, and it has a motor in it. At each time that we start or stop the tape recorder on the spacecraft, believe it or not, it torques the whole spacecraft around. Okay? A problem. And we see on the chart here what happens. Here we are in our normal limit cycle. About this point in time right here, we say we start the tape recorder. And what happens is, if we're going in this direction, it drives the the whole spacecraft over hard. And you see a very steep...
It bounces back for a while.
Very steep. And then it bounces back hard, and we have a lot of firings and a lot of steep motion here. Steep motion means fast motion of the camera, the spacecraft, and therefore the camera. And that means a lot of smear. How do we overcome that?
You've got to use a tape recorder for most of your pictures.
That's right, especially at this encounter. You've noticed we've used the tape recorder a lot. And what we've done is that each time that we get to this point where we have a start or a stop command, we simultaneously on board the spacecraft, in addition to commanding the recorder to start and stop, we send a command to the attitude control system to fire the right amount of thrusters in the right axes to just compensate.
So you finesse this torque a little bit.
Absolutely. We cancel it. And that's what we call momentum cancellation.
Very good. Okay. And
so those are the things having to do with the camera motion. Now we have to talk about the target motion. And
we're going by at 33,000 miles an hour.
And we're going mighty close to Miranda. Obviously, we have the same problem as the photographer taking a picture of a race car. Okay. And the solution is identical. What we do, here's our Miranda, if you will, moving by. We do this with several other satellites also. And what we do is, with the recorder playing, we slowly move the spacecraft, the whole spacecraft, not the scan platform. The scan platform would be too jerky if we did it, but we move the whole spacecraft very slowly. We literally track in the field of view of the camera the target. And then what is happening, you can see when we move the whole spacecraft, we're depointing from the Earth.
That means the antenna is no longer looking home.
That's right. And so that's why we have to, it's one of the several reasons why we have to record. And we've heard a lot about image motion compensation, target motion compensation, same thing.
This is it. I understand you do that. You do that with gyros by you go on gyroscopic control and you feed the gyroscopes a slight signal says you're wrong, and they continuously try to correct for it very slowly.
Very slowly. Basically, what we're doing is faking out the attitude control system.
And tomorrow we'll see how well you do.
I think we're going to do great. We've had several tests, and the lack of smear in the images that we see tomorrow will be demonstration.
Very good. But you have tested this system then?
Absolutely. We've used it some in tests using star backgrounds on the way to the planet.
Thank you very much.
Sure.
Yesterday, Lonnie Lane told us about an experiment called star occultation. That's where a star passes behind Uranus rings, and Voyager's photopolarimeter measures light from that star. The experiment took place late last night, and Bill Griffith was there.
The plan was to use the star Sigma Sagittarii to backlight Uranus's rings with Voyager's photopolarimeter. Scientists would take as many as 100 images per second, giving them a very clear image of the ring's true structure. The first critical moment in the process came late last night as Lonnie Lane and his team waited for confirmation from Voyager that it was all set to perform the occultation.
Tonight we're right now trying to see, will the instrument set up in the proper field of view? The instrument has several different size of apertures. It's on a wheel. We've been having some trouble with that wheel because some polymer buildup on the electrical contacts, so it slips and sticks. And in the past we've had some difficulties. So we just executed about 2 hours ago a sequence that rotated the wheels back and forth, end to end, very slowly, and allowed them to try to clean themselves. And then we have 3 measurements that try to address itself to the 1 degree and then back to a safe. And we hope that'll do the last cleaning, and then when we set up, we'll be in the right place.
One potential problem added to the drama, the tracking site in Madrid, Spain, which would be receiving that critical occultation data from Voyager, was under a cloud and rain was forecast.
The weather situation is such that the data we're bringing down has very little protection code on it. We're operating in the type of data mode that does not have extra Reed-Solomon coding and other things to protect the data. So at the data rate we operate, we're very sensitive to water vapor and rain especially. If it rains, we're in trouble because the data will not make the antenna with enough energy coming through to let us get the signal and lock up. Now, the predictions were relatively nice weather in the latter part of the day at the Madrid station, seeing potentially some rain. So we've been very carefully balancing when does the data come down that's critical relative to when the rain might start. The problem is Spain does not have large-scale weather patterns that are very small localized. The weather can change in 45-minute centers. This thing lasts almost 4 hours. And it's a gamble. If we try to protect the data by a real-time command, we would lose one of the supporting experiments. And so I guess we decided to sort of go for broke, hope the weather's okay, and try to get both experiments to measure at the same time.
So Lane and his team spent a few anxious moments waiting to see if their 4 years of planning would be successful or all for naught.
Everything together, yeah. See the clock. If there had been a change. Plus 15. You wanted anticipation, you get it. This is a watch hot.
Then, around 10:45, they got their answer.
Data's on the ground now. There.
All right, to all my friends who made this one possible, thank you. Let's see if we get some good data on this.
This morning, Lane and his team were still on the job, poring over the clear images of the rings that Voyager had sent back. And the good news was it hadn't rained on their parade after all.
It didn't rain. We had a very small amount of interference. Things worked very well. We have most of the data we want. We crossed the total of 2 rings inbound, 2 rings outbound, the same 2. They are different. We see geometry changes. We see extremely interesting fine structure. I think we're going to give the theoreticians a field day trying to explain some of the fine structure we see. That is, the gross models will probably fit with the data. But in fact, the very high resolution in the rings is going to cause some theoreticians a few sleepless nights trying to understand what happened and why.
At JPL, I'm Bill Griffith.
Those were exciting moments for Lonnie Lane and his team. Now, Lonnie's here with us to tell us more about it. Lonnie, how did it all work out? I understand there were a few sort of nervous moments.
Yes, every occultation we've worked on so far has had them. The sticky wheel was one question, the aperture. This time it's set up just properly for the Sigma Sagittarius occultation. We got right where we wanted to be, and you saw on the film that everybody was very pleased. We realized a large team has worked very hard to make that happen, including a real-time command sequence that got fit into the spacecraft barely 2 days before closest approach. So a lot of hard work on that.
And then there was also a little bit of a scare about weather over the tracking station that was perhaps going to cut down the data.
That's right. This particular data set had very minimal protection on it, minimum code protection, and we're very susceptible to weather. If it had been raining, we would have lost the data, and there's no tape recorder on this set because we need it for near-encounter images. So it was a nervous few minutes, but apparently everything worked out fine.
And you did get the data back. Now, the data is now back. You've had a chance to look at it for a while. What do you think?
Spectacular things. The resolution of this occultation, the Sigma Sagittarius, across just two of the rings of the outer part of the 9-ring system, the large epsilon ring and a very narrow, small delta ring. The interesting thing about it is that there are certain limitations from the ground in the optical domain, mainly because the size of red stars used by ground occultations, or potentially from space telescope or very large aperture things in Earth orbit. So it's sort of limited by the physics of the way light diffracts around particles in a ring system, which says on the ground or in Earth orbit, for everything except maybe a super long-range baseline radio system, you're limited to about a kilometer resolution. And some of these rings...
Anything smaller than that is just a fuzz.
There's going to be a fuzz and ill-defined at best. With this particular occultation, because we're so close, and high sampling and using a relatively small UV light source, a star, we were down to 10-meter resolution approximately. And as I say, that's much better than anybody's going to have for a long, long time. The structure inside the epsilon ring is extremely complex, and we're trying to sort it out based on models similar to things we've learned at Saturn. Question of whether some resonances or the shepherding satellites or embedded satellites cause these kind of very rapid oscillations in the density of material in the rings.
Is it, now that you see it in the finer structure, is it one ring or are there breaks in it?
At the moment, we have seen no breaks, so it's sort of at least at the underlying level of potentially fine dust, it's continuous. What we cannot separate out from our experiment is are larger particles, baseball-sized or meter-sized objects, or maybe even larger, segregated into channels within the large ring structure, or maybe a 15-mile-sized ring. To that end, we're dependent upon the radio experiment, the radio occultation is occurring right now, to sample out the larger particle domain, and then we assimilate the visual images, the radio science data, the photopolarimeter data, together to get a span of particle sizes and then the nature of the way everything fills together and makes that system work.
You're going to have another occultation of the ring system.
That's right. It's completed. We've seen our first quick look of it, but only half of it because most of it's on the tape recorder.
That portion is tape recorded.
That portion is tape recorded, right. And so we will wait to see it when it comes down.
And from the first quick look, does it look again like a complicated structure?
Yes, indeed. We have all of that and maybe some very nice surprises. We've got our fingers crossed, a little bit more data analysis, and next day or two, those stories should be coming out.
Thank you, Ronnie.
You're welcome.
Of course, there are other experiments that have plenty of suspense for their science teams, too. One of those began early this afternoon and ended just 14 minutes before we went on the air. David Sparks visited the radio science team as this report.
Television shapes all of our lives as an information source. This is underscored by the fact that we are watching the encounter between Voyager 2 and Uranus on television every night. Well, the people in the radio science department of this entire venture might suggest that they have an awful lot to contribute to this mission as well.
What we do is we use the combination of the spacecraft, the ground station, and the radio signals traveling between the two as a probe to measure, to reach out and touch, if you will, these remote planetary bodies. While Voyager 2 is passing behind the Uranian system, it first passes behind the rings and then behind the atmosphere. The radio waves from the spacecraft to the Earth will be passing through the rings, received on Earth, then passing through the atmosphere and received on Earth. We measure on the ground at the Earth station in Australia the characteristics of those signals.
From an intuitive point of view, it might seem that the imaging team, because they use cameras, would gather more information about the physical size and shape of Uranus and its associated structures. Dr. Len Tyler and his team of radio science people put an immediate end to this notion.
Our measurements are much more abstract. They're quantitative, and they relate to structures that can't be seen in the images. For example, we're sensitive to the size of the particles in the ring system. Those particles may be in the size range of marbles or ping pong balls up to boulders, and those are far below the resolution of the images. In the case of the atmosphere, as the radio wave cuts through the atmosphere, we penetrate to levels that may be below the visible portion of the atmosphere, or may be in parts of the atmosphere that are transparent.
Dr. Tyler's team has been preparing for months to gather data during the Voyager 2's period of occultation, when it disappears behind Uranus. The months of planning turn into a few hours of very intense excitement.
In the case of the rings, we learn about the size of the ring structures. We learn about the size and the distribution of sizes of the ring particles. We should be able to make extremely precise measurements as to where these rings are located, certainly on the order of 100 meters, which is about the size of a football field.
Let us try to put this all into perspective. Measuring objects the size of a marble and locating rings within 100 yards over a distance of 2 billion miles, 8.5 years after the spacecraft was launched, one wonders if you really can put this all into perspective. I'm David Sparks.
The occultation by Uranus ended within the hour, but we're still waiting for the second ring occultation, and now Von Eshelman of the radio science team has dashed over here to tell us about it. And welcome, Von. What can you tell us this early in the whole process?
Well, we're very excited. The very complex maneuvers of the spacecraft to keep it pointing in the proper direction as it went behind the planet. And also, during the time that it went behind the rings, we know we have data and that the spacecraft came back to the correct position after it cleared the planet. And for several hours now, we've been taking data. I actually left before I saw the signatures of the rings coming out, but I saw them going in. We see every one of them. We maintained a signal all of the way through the occultation. Now, when you think about the fact that we're about 2 billion miles away, transmitting from a spacecraft with about 20 watts of power, where the atmosphere refracts the signal in a way that diminishes that power by a factor of several hundred, it's as though you're dealing with a tenth of a watt over a couple billion miles and picking it up and not losing it during the time that the spacecraft was behind the planet.
So the signal's here. Now you have some time. You can relax and analyze it and tell us what's the complete structure of the atmosphere of Uranus.
Well, the support team and the science team and the people in Australia are just so happy that everything has turned out so well.
You have a diagram here showing how that power cuts off when we go behind it. What happens?
Well, just let me illustrate the rings first. We have a view of the plane of the sky with the spacecraft moving from the right side to the left side with time. Spacecraft right now is about in this position in the plane of the sky. It has just cleared the rings coming out of the occultation behind them. The circles are indicative of the size of the antenna beam, but that's not too important relative to the ability to make measurements. We did see the rings illustrated here just with some marks going in, and the signal strength was reduced as much as 15 decibels, which is a factor of about 30, another about 3% of the power that it would be without the ring there. That immediately tells us, for example, that these are not dust rings. There are substantial sized particles there. The atmosphere itself, and let me say a few more words about it in the next illustration. It's a little bit better to talk about the atmosphere. Here, blowing up that central part, again, the spacecraft trajectory is from right to left. Now, it then passed behind Uranus, as seen in the plane of the sky. And the distance, when it's right at this position, for example, the direction to to the limb where we see it is about 3 degrees off the direct.
Now, do you re-aim the spacecraft?
Yes, the spacecraft now must go into a complicated dance in space in order to maintain the direction to a very high precision to aim at this point along the limb
You
of the
actually
planet.
track right along the edge of the planet.
Now, that looks very similar to what some of the logos on some of the television programs have about a glint that goes around a circle, if you've ever seen those things. That's what you would see as your eyeball. If you could see the radio waves, there would be a strong glint moving along the periphery. It moves faster when it gets to this point. In fact, even though the spacecraft is going in the plane of the sky only about 8.5 kilometers a second, that glint is moving at 20 kilometers per second.
And so from the data gathered up along this curve, we can now tell something about what is doing the absorbing in the upper atmosphere.
Yes, it's primarily the question of the structure of the atmosphere. It's temperature and pressure.
So thank you very much, Ron. Uranus, just like Jupiter and Saturn, has rings, but Uranus rings are as dark as charcoal we use in our barbecues. In fact, they were only discovered by noticing how faint starlight from behind them was cut off as it went through them, much as it was in this experiment we just conducted. They weren't discovered until 1977, and the first photographs of them weren't taken until 1984.
The rings of Uranus. Then I think it would be fair to ask you how the rings of Uranus compare to the rings of Saturn and Jupiter.
Okay, well, our ground-based photograph actually came only in the last year or so, and the rings were discovered in 1977 from the ground.
But you photographed them.
Stellar occultations, right. What we learned from that data are that the rings are significantly different than the Jovian ring system and the Saturnian ring system. Different in the way that the known rings from the ground are very, very thin, almost like little necklaces around the planet with very, very much open space between them. Now, at Saturn, we of course, found a ring system which was full of material and a very colorful structure, very colorful, very variegated in style and texture. At Jupiter, we found a very, very thin ring associated with 2 or so moonlets within them. Now, one of the big mysteries that we've had for a long time from the ground was why do we not see an association in the Uranian ring system with satellites, with moonlets, as we do at Jupiter and as we do at Saturn? So one of the exciting things about this project is that we want to go there to look for those moons associated with the rings. We know that the moons of Saturn, for instance, give you all of that undulating detail within that ring system. So now that we're finding new satellites around Uranus, we're hopefully now going to associate that with the ring structure. And associated with these new moonlets, of course, we may be unfolding, even now, new ring structures as well.
The research that is taking place up in the spacecraft is on a recording device, right? When you start getting all of that back and looking at it, can you give us a guess as what you're going to see? Is it possible? Is it fair?
Well, it's a madhouse right now in terms of analyzing the data. We're getting back new information. Each picture we get literally is something new that we've never seen before, and I think that's going to typically in these encounters, the one thing that happens is that we get a lot of unexpected results, and it takes sometimes many months to unravel it all. But certain things you can get right away. New ring structures, new moonlet structures, and these interactions are coming moment by moment now.
You wouldn't want to guess how many more satellites you're going to find? How many? And there may be a lot more rings, you say?
Could be, yes.
You hope?
We hope.
Because that's your area of expertise,
well,
isn't it?
From the ground, we know that there are these thin, almost easy-to-see rings because there's a lot of material in a very, very small amount of space. But these broader rings, which have very little material, they're thin and translucent, are the ones that are harder to see, and the ones we can see as we get back behind the planet and see them from a different sun angle.
It's an exciting time for you, isn't it?
It's very, very exciting.
I can tell you love your work.
Yes.
And I'm enjoying what I'm doing. It's been a pleasure talking to you.
Thank you.
I'm George Fenneman.
Rings of Uranus are indeed a puzzle, and to help us solve it, we have Rich Terrell with us here. Now, Rich, what have we learned in the last few hours?
The last few hours, we got our first images right around ring plane crossing. Of course, the best images will come down tomorrow. The images in ring that were taken at the moment of ring plane crossing.
Looking right along the plane,
right.
The ring plane, one behind the other.
Right. And what's nice about that geometry is that the rings are very compressed, and with one image, we can look down the entire long length of the ring system, looking for shepherding satellites and for faint ring material.
And the shepherding satellites, we found a couple of them, haven't we?
Yes, so far we found 2, and we expect perhaps we'll find others. We have our best sequence for finding the shepherds has already occurred, and we're in the process of searching through that. We found two fairly large ones.
Except you have one of the pictures that shows them both at the same time, which seems like an almost magical coincidence.
Right. We were lucky in that, but we have two satellites, one on either side of the bright epsilon ring, one inside, orbiting between the rings. And in fact, this satellite solves one of the mysteries, and that is, are we going to have two shepherds for each ring, or can we share a shepherd? Quite clearly, the epsilon ring and the next ring, the delta ring, can share this shepherding satellite.
It's about equally spaced, roughly equally spaced between them, isn't it?
Right. We have a close-up view of this inner shepherding satellite, and it turns out that we can now resolve the satellite. And it's somewhat larger than we expected, and it's about 30 kilometers in diameter, and it's as dark as a piece of charcoal.
The same, then you'd guess it might be the same material as we're seeing in the rings.
Could very well be part of, or the same material that the rings are.
30 kilometers is a pretty good-sized object. That's bigger than a lot of asteroids.
Right, right. It's amazing we can photograph something as dark as charcoal against the black background and the light.
This particular picture here is absolutely gorgeous, but somewhat confusing. What am I looking at?
Okay, we're looking at a color process here. It's a color average of the rings. So what we did was we had to add up all the light from an entire image across many thousands of kilometers of ring and essentially make one line of data, a radial profile in color. We've extended that radial profile across the entire image to make kind of a pseudo picture of the rings. But what it does show is that the bright epsilon ring here is colored white or neutral. It seems to have a gray color. But the interesting thing about it is the other rings do show color differences, and this is quite unexpected.
Really? We saw color differences in the rings of Saturn, for example.
Well, the rings of Saturn are quite a bit more massive, and perhaps there are different processes acting on them. We know that the rings of Uranus are all quite dark, and at least what we knew from ground base, they were we thought they would be fairly uniform.
Ah, I see.
But we're finding that rings, these two rings, the delta ring and the gamma ring, which appear to be quite similar in most of our previous imaging, appear to be different colored objects.
Does this imply that they come from different sources?
Well, we don't know. That's one of the mysteries we're going to have to think about for quite a while, and perhaps some of the other data, high-resolution data, will help us resolve that.
Because perhaps a completely different material then might have broken up to form each of these rings. Or something of that sort.
That's right. The mass of one of these rings is comparable to one of these shepherds in terms of size.
Thank you very much. We're getting pictures from Voyager that could be called historic in their importance, and I thought I'd take just a minute to show some of them to you. So relax and watch as we take a short trip through some of the pictures over the last few. This is just Uranus from a long way off, taken some time back. This is a small moon Miranda. It is very exaggerated in this view because this particular one was taken to help the navigation team. This is the moon we're going to come very close to, and in order to find out exactly where it was against a star background. Now, not all those white spots are stars. Some of them are just noise. We took this picture of it. Ariel, this is one of the closer ones we got before those that were taken this afternoon that were recorded for later playback. And another picture of Uranus. Several of these were made at the time we were also looking at them with the spectrometers. The rings, another view with some light of Uranus shining on the innermost portion, and the moon Umbriel, one of the others we'll get a closer picture of. Uranus again, and here rather sharp filtering to bring out some of the atmospheric characteristics. And Oberon, finally, Titania, the one we showed you at the opening of the show. And now back with us once again is Dr. Ed Stone, the project scientist. Ed, let's try to recap the day if we can. And what would you say has been the biggest accomplishment today?
Well, I think the major accomplishment has been actually having the spacecraft execute, as far as we can tell, exactly the plan that we had laid out, and including, as we've heard, the very, very precise radio occultation, very complex set of activities on the spacecraft. Everything so far has been going very well, and that has been certainly the major accomplishment today.
It has indeed. It's been a phenomenal mission. After all the changes we made, sending the commands right up to the last minute, even after it was executing the last series of commands, we modified it. Mm-hmm. It accepted all this.
That's right.
And the discoveries we've made today, of course, the magnetic field stands out. Do you have any expectations about the pictures we'll see tomorrow? It's sort of
Well,
It's gonna be
of course,
exciting business.
the main imaging that's returned tomorrow will be the best images of the satellites. They'll be coming back tomorrow afternoon. And as we've discussed before, there are some features which show up in these images that we have to date, which are rather low resolution, which look like they may be impact craters with rays. And there are other features on the satellites which are not recognizable. And that may mean we're in for some surprises once we, in fact, can image these things carefully enough to see whether these are just colors on the surface or if, in fact, there's topography, there's relief associated with these features.
One thing we have touched on very little is your own specialty, cosmic rays and
Yes.
charged particles. Could you say just a little bit about how that's going, how those investigations are going?
Well, we're currently right in the magnetosphere. We're measuring the trapped particles, the particles which are spiraling around the magnetic field, bouncing back and forth.
Like our own Van Allen radiation belt here.
Exactly, like our own Van Allen radiation belt. And what we're trying to do is determine exactly what the shape and configuration is of the magnetic field and of the population of particles trapped in that magnetic field. And again, we're now more than halfway through, but we haven't gotten the data for most of the magnetosphere yet. That will be coming back tomorrow as well.
That's also being recorded?
Yes.
Mm-hmm. And what about the higher energy cosmic rays? Are they also? They're also affected by the magnetic field, aren't they?
They're excluded by the magnetic field. In fact, during this time, our sensors will be mainly responding to the particles which are trapped inside the magnetic field.
The lower energy.
Mm-hmm.
And also there's various waves, plasma waves, and other phenomena going on. How are those experiments also giving us information?
Yes, again, especially the plasma wave device on planetary radio astronomy will be, we may well find something quite different on the dark side of Uranus than on the sun side. There's no reason to expect the two should be different because the sun side is in the sun for so many years at a time, while the dark side is very, very dark for a long time. It may turn out we'll have a rather different ionospheric mechanism there, and we may well have a much different magnetospheric mechanism associated with this long tail.
Spreads out quite a ways behind.
Yes.
Thank you very much, Ed. So we come to the end of the day. We have seen some new evidence about the nature of the atmosphere of Uranus, and we've heard the first direct evidence of a magnetic field which surrounds that planet, and one which we hope very much to find. Well, we won't be here tomorrow. We'll be back the same time Sunday evening, however, as we continue to watch the encounter of NASA's Voyager 2 spacecraft with the planet Uranus. And please, won't you join us then?